In this video, I'm going to go over some transformations that appear on the IB Math SL exam, mostly through examples. So just the first slide has some notes here about all the possible transformations that like to get tested about. We have transformations to any kind of function. It could be a parabola, it could be an exponential function, it could be some unnamed function where you just have a shape on a graph. And these are some things you can do to the graph of the function. You can shift it up and down. That looks like adding a constant at the end of the function. You could shift it left and right, and that looks like adding a constant inside, usually inside parentheses or right to the x. You could stretch it vertically, and that looks like multiplying by a factor in front of your function. You could stretch it horizontally, and that looks like multiplying by a factor just where x is in the function. You could reflect it, really common reflection over the x-axis, or an up-down reflection, and less commonly you could reflect it left-right over the y-axis, and that looks like a negative inside the function where x is. So let's see some examples. Describing transformations in words, these are usually like one part of a multi-part question where they're looking for as precise vocabulary as you can give them. So describe the sequence of transformations performed to the parent function y equals x squared to get this graph. So it's just a modified version of the parent parabola. Y equals x squared is a parent function. It has a vertex at 0, 0. It's sort of your most basic parabola. It rises up. It has a point 1, 1 on it, because if you plug in 1 to x squared, you get 1 as the output. It has the point 2, 4 on it, because if you plug in 2, you get 4 has the point 3, 9, and so on. So this one has two transformations applied to it. It has the 4 being multiplied by x squared, your original function, and it has the minus 3 being subtracted from the function. So the 4 is a vertical stretch. So you want to say that this is a vertical stretch by a factor of 4. That's the correct language to use there. We aren't asked to actually sketch it, but that would mean that it would stretch out and become a taller, skinnier parabola, like that. And then the negative 3 here, this is a vertical translation. Basically, it's a slide up, down. Let me put the word translation. And it's good to indicate how many units and which direction. So it's a vertical translation, 3 units down. So because it says minus, it's going to move the entire graph down 3. It's not here, just to indicate what the difference would be. If that minus 3 was inside parentheses with x, that would make it a horizontal translation. So just in case you're trying to figure out what is the difference between the two, that's what a horizontal translation would look like. Another question here, we have a function shown to us on a graph. There is no function given in the question. It just says the graph shows y equals f of x. So it could be any function, looks like a cubic function. And then for each part below, it's asking us to copy this function and draw the new ones. So below we have y equals f of negative x. So we have to know that that means all x values are becoming negative x and y's are not changing. So for example, there's a point here at negative 3, negative 4, which would now be located at positive 3, negative 4. In fact, let me change colors for my transformed version. We now would have a point at positive 3, negative 4. That's the point that used to be here. We could pull out a couple more. The point that used to be there at negative 2, 0 will now be at 2, 0. The point that's right on the y-axis will stay on the y-axis because the x value there is 0 no matter how you look at it. The point that is at 4, 0 will now be at negative 4, 0. And we'll pull out another one. The point up here at 5, 3 will be at negative 5, 3. And so we can connect the new points. I'm going to erase these open circles that I had. And we can connect the new points to make oops, I should have gone more smoothly through there. Try to get down to this point here, like that. What this ends up being is a reflection, left and right reflection over the y-axis for the original function. I guess I should have stopped about there, right? If you look at where it stops over here. So this is the idea here, sketching transformations without having a function to work with. You might want to pull points from the graph and then imagine doing the change to them. So for example, this one, adding 2 to the function, means taking all y values and adding 2 to them. You can imagine doing that with a few points the same way we just did. So if you have the old point is here and you want the new point to be 2 units higher, then it's there. have an old point here. You want the new point to be 2 units higher, so it's going to be here, and so on. So you'll end up doing that to a whole bunch of points and getting your new higher version of the function. That's my favorite preferred way to do transformations of functions on the graph. Pick out a few points and do the modifications to them. This one's a little bit trickier because when there's something inside the parentheses with x, you have to do the opposite of what it says in the function. So if it says 2 times x, you will actually have to divide each x value by 2. If it said x plus 4, you would actually go -4. So you'd move it to the left by subtracting 4. So if it's inside the parentheses, you must do the opposite of what it says. But if it's outside of the parentheses, like this -1, you'll do exactly what it says in -1. You'll go down for all your y's. So the 2x, if I'm taking a point and trying to transform it, the point that used to be here is the x coordinate of it is going to get cut in half. So it's actually going to move to about here. But then it's also getting shifted down 1. So it's actually going to be here. So that's the new version of the red circled point. And then you have to do the same thing with all the other points. So let's pick out just one more for the sake of showing it. So if you had a point there on the original function, the x value is getting cut in half. So it would be moving to here, and then it would be moving down 1. So you're taking your values and you're making these modifications to them. This one's going to end up looking like a shrunken version of this graph that is also shifted down 1. Sometimes you're asked to do transformations with trig functions. This requires a little bit of extra knowledge from our trigonometry section. So here's a graph of a sine wave. I have no way of knowing its sign except for that it tells me it in the question that it's a sine function. This asks me to enter the correct values. That's because this is from a computerized test. I'm not going to enter them, but I'm going to find them, the correct values for A, B, and C. But I just wanted to put this in this presentation because these values are transformations. You don't have to think about trig as being a completely separate topic. It does involve the same sort of knowledge about transformations that we have been talking about in this presentation. The B value is a little bit trickier. So for the A value, we're thinking about it, for trig, we like to think about it as the amplitude of our function, absolute value of the amplitude. So you're thinking about your wave having a midline. The midline here is that blue dotted line I just drew. Now, normally the midline for sine is right at 0, and the height of the wave is 1. So if it's anything other than 1, that's going to show up as a vertical stretch. The height of this wave, as you can see, is 2. So our A value is going to be 2. It is a vertical stretch. Our C value is going to be that vertical shift that I just said. The midline is usually at 0 for a sine wave, but this one is up at 1. So we have a +1 as our C value. The whole thing has shifted up 1. And then for B, for a sine wave, we actually cannot see a B value from the graph. We want to think about the formula period for sine equals 2 pi over B, because the period we can see from the graph. We cannot see B, we can see the period. The period is how long it takes in the horizontal direction to complete one wave. So from here to here, we have a completed, where does that end here? From here to here, we have a completed wave cycle. I can see it's pi on this graph. So that means I can put that pi in here and solve for B. So these are the procedures that we tend to use on trig functions, but I just wanted you to see them in the context of a transformation lesson. So in that case, B is 2. So the other values you can find from the graph, but not B. And then they also like to mix transformations with vectors. So here we have a function f of x equals x squared. We have another function g of x. It's a different kind of quadratic. You can see it has transformations. First thing it asks us to do in part A is give a full geometric description, so talk about the movement of each of the two transformations. So you can remember that the number in front is going to do a vertical stretch. So we have a vertical stretch by a factor of 2. And what else do we have? We have a -1 inside the parentheses, so that's going to be a horizontal translation. 1 unit, and it's to the right, because you do the opposite of what it says if it's inside the parentheses with x. And then part B says the graph of g is going to be further translated by a vector, 3, -2. So what that means is that 3 is a horizontal and Negative 2 is a vertical additional slide that's going to be happening to it. So when you translate something by a vector, it basically means whatever your graph is, you're going to take each point and do the same vector to it, right? So that you get this sort of new curve, and it ends up just being a slide. A horizontal shift in your horizontal component of your vector and a vertical shift in the vertical component of your vector. So in this case, we'll have to think about this thing moving 3 more units to the right and 2 more units down. So we have a question asked to us. The point -1, 1 on the graph of f is translated to the point p on the graph of h. We're supposed to find the coordinates of p. So this is a lot of movement going on. If we have the point -1, 1 on the original graph, which we do, first it's going to go get shifted in accordance with g. So it's going to get translated through g first. And g, we know, has a horizontal translation to the right 1 unit and a vertical stretch by a factor of 2. So the point -1, 1, when it's on the f function, when it's on the g function, x value is going to be 1 unit to the right. So now it's going to be at 0. Because I was at -1, I'm shifting it 1 unit to the right. The y value is going to get times by 2 multiplied by 2 because of the stretch factor of 2. So that same point on the g function is 0, 2. And then for the h function, it's going to have this further transformation where it's going to be slid 3 more units to the right and then 2 units down. And so the point P on the graph of h is going to be 3, 0. It's kind of a tricky concept. And that's that.